Dear students, today we will talk about Fresnel diffraction at a circular aperture. I have provided the link of another video in the description which talks about Fresnel half period zones. So I'm writing Fresnel half period zones. You should first go through that video in a detailed manner and try to understand what are Fresnel half period zones and how do we obtain the maxima and minima pattern of the diffraction using this Fresnel method. Okay, once you have done that, then you can go through this topic called Fresnel diffraction at a circular aperture. So this is a source of light S. It is emitting light rays in all directions. It is a point source. Then we have a slit wherein there is a slit of this circular shape, and then we have a screen at certain distance from this slit. We know that light rays from the source are hitting this aperture, circular aperture. What will happen due to diffraction? All of us understand that light also goes into the geometrical shadow of the object. Normally we would expect light only in this portion, in the portion which is parallel to the slit, but we know that on account of diffraction light bends even in the regions which fall in the geometric shadow. So at this point light will bend not only this way but also this way. A simpler way of presenting this diagram would be that this is the slit. Okay, because it is a circular aperture, we say it has a diameter say d and a radius say r. Half the diameter, that is radius, is this much, and this source is placed at a distance a from the slit and the slit is placed at a distance b from the screen. Now dear students, you have always seen it that whenever we are interested in understanding the diffraction or interference patterns, whenever we are interested in finding the minima and maxima of those bands which are formed on the screen, the most important thing that we want to find out is path difference. Okay, path difference between any two rays of light which meet at a point. So let's consider two paths of light. One is the straight path that hits the screen at the center, and another is this path. So there is a light ray which reaches the edge of this aperture. Then from this point, on account of diffraction, it bends and meets at the same point. So we are essentially interested in finding the path difference between this SO, and suppose this point is P, this is Q. So we are interested in finding the path difference, and let us denote the path difference by delta. This path difference will be SP plus PO on one hand, SP plus PO minus this much, SO minus SO. And we understand that what is this SP equal to? SP plus PO, what is SP? It is A square plus R square under root. So it is A square plus R square under root. And what is this PO? What is PO? It is R square plus B square under root. So it is B square again plus R square under root minus SO. And what is SO? It is A plus B, the straight line distance, A plus B. Now let us try to simplify this equation. We can take R as common, okay, or A as common. What we are left inside? So it is 1 plus R square by A square, okay. And here we can take B common. Taking A square common means the square of the power will be cancelled with this root. So we are taking A as common, okay. So here we have taken B as common. We are left with 1 plus R square by B square under root minus A plus B. Now we can use the formula to expand it, binomials theorem. So 1 plus power will come down. It is 1 by 2 R square by A square plus B times 1 plus 1 by 2 R square by B square, and then we have minus times A plus B. So once you take this A plus B common, it will get cancelled with this minus A plus B, right? So we are left with this term only, second term here and second term here, okay. So this A and one of the A's will get cancelled, B and one of the B's will get cancelled. So you are left with, so delta is equal to how much? So this will be R square by 2A plus r square by 2b. Then we can further take this r square by 2 as common, and we are left with 1 by a plus 1 by b. So this is delta. Now if you go through that Fresnel half period zone video, there you will understand that suppose if this circular aperture contains n half period zones, n half period zones, then what will happen? This path difference will actually be how much? Equal to n lambda by 2 half period zones, n times. So we can write that this n lambda is equal to 2 delta. So you can put this value here, okay, in this equation, 2 delta, okay. So you can also rewrite this equation. Let me do it again. So this was equal to 2 delta, okay, by r square is equal to how much? 1 by a plus 1 by b. For 2 delta you can write n lambda, okay, by r square is equal to 1 by a plus 1 by b. So this is the main equation that you obtain once you have placed the slit at certain distance. Now it can also so happen that you have placed this slit at a far off, this source at a far off distance. Here it is at a finite distance, a known distance. But suppose this source of light is at a far off distance. So in that case we can further manipulate it. So we say that if the source of light is at a far off distance, and what do you mean that it is at a far off distance? See, here you could guess it easily, that suppose this source of light, which was a point source, it was emitting light rays in all possible directions. So the wavefront that we could imagine would have been a spherical wavefront. But once this source of light is far away, all you can say is that the wavefront will be plane. It will have a plane shape, right? So what will happen in that case? Look at the diagram again. In that case, what will happen? Because we are saying that S is far off from the slit, this A will be infinity. Okay, so once A is infinity, what happens? So once A is infinite, 1 by A is 0. So this equation reduces to 1 by B is equal to n lambda by r square. Okay, so n is how much? Because we are also interested in n, the number of half period zones that are inside the circular aperture. So n is equal to how much? R square by b lambda. You can further multiply and divide it by pi. So it is pi r square by b pi lambda. What is pi r square? It is the area of the circular aperture. So that is all. Now the intensity pattern that you obtain on the screen will be bright or dark. These are the only two possibilities. It will be bright or dark. It depends on whether n is even or odd. It also depends on whether the source is near to the slit or far away from the slit. To understand that, I am telling you once again that you have to go through this video, Fresnel half period zones. There I have mentioned in detail how do we find the maxima and minima intensity patterns on the screen. Because the result of any diffraction or any interference is that we obtain alternate dark and bright bands on the screen. Any bright band of light will be called as maxima and a dark band of light will be called as minima. It depends on whether the value of n was even or odd. But it also depends on whether source was near to the slit or it was away from it. So to understand that in detail, you will have to go through this video. Otherwise, it is a very short topic. Okay, I'm taking a cursory look at it once again. So it was Fresnel diffraction at a circular aperture. This was the source of light, this was the slit, and this was the screen. To make the diagram simpler, we made it this way. The distance of the source from the slit was A, of the screen from the slit was B. Then we tried to find the path difference, which was denoted by delta, path difference between this path of light and the straight path of light. Okay, so this path was consisting of two parts, SP and PO. We found that from the two right angled triangles, and SO simply was A plus B. So we subtracted this from this, and then we used the formula binomial to expand these terms. These terms were getting cancelled and we got this. Okay, next to this we got this. How many number of half period zones were there in the circular aperture? So they were given by n lambda by 2. So n lambda was this much. So you have substituted it here. Okay, then we have, this is the final formula in fact. Then we have manipulated it a little, that if the source of light is far away, then this term reduces to 0 and the formula reduces to this much only. Okay, so this is how you can do it.